Hello, 6th grade scientist. This week we're going to fast forward a little in your energy fill in the blank book to pages 9 through 12. So from page 9 to the end of the book, we're going to do lessons about energy and work and simple machines, complex and compound machines. So basically, I want you to start on page 9. In the top part of page 9 right here, this actually goes with the previous lesson. So we're not going to look at that yet. We'll be doing that later. That's a conduction, convection, and radiation lesson. We're going to start over here where it says energy and work. I'm going to give you a couple answers on the answer sheet so that you could just fill them in, and then we'll go and talk about it. I want to make sure that you get these answers in the right place. So let's begin. What is energy? Energy is the whole reason for the unit. And every single time I talk to my students about energy, I say, okay, it's called the energy unit, but do you know what energy is? Most often, they don't know what to tell me. So I want you to memorize energy is the ability to do work. Energy is the ability to do work. Right here in your answer guide, you should be writing energy is a property that enables something to do work. Work means these things, two things: to apply a force to an object over a distance. So you have to use force and apply it over a distance. That's the first thing that you need to have in order for work to happen. And we're not talking about work like a person goes, oh, I went to work today. We're talking about scientific work. The definition of scientific work. How a scientist views work. And that is different than your dad going, I'm going to go to work today. So, energy is a property that enables something to do work. You should have this answer and this answer filled in. And work means to apply a force to an object over a distance. Apply a force to an object that moves it a distance. Over a distance. And number 2, the object moves in response to the force. So the first thing is to apply a force to an object over a distance. And then number 2, the object actually moved in response to the force. If something has the ability to cause a change in motion, it has energy. Energy can cause work to be done. So when we see work done, we see evidence of energy. And evidence of energy is when work is being done. For example, when a toy car at rest is pushed, work is being done on the car if it moves. So when a toy car, if it's sitting still, all of a sudden is pushed, we are putting work on that car if it moves forward. Because our definition of energy was, our definition of work was to apply a force. Did we apply a force to the toy car? Yes, we did. Did it move a distance? Yes, it did. If you push on a toy car, it's going to move forward. So if the object had a force applied to it and it moved a distance, force that moves an object a distance, we pushed the toy car, it moved a distance. So we know that work has been done on that car. Scientific work. When a fan is connected to an electric circuit, it moves. So work was done on the fan. So, what is work? Work equals force times distance. Work equals force times distance. Now the items that are in this little rectangle, you need to know these. These are majorly important and you need to copy them down. You will need to know this to figure out any problem concerning work, force, or distance in this unit. So the unit that we use for force is a newton. The unit that we use for work is called a joule. It's not spelled like jewelry. It's Joules. And the unit that we use for distance is called a meter. So, we use meters, just like if you were to put that something was 1 centimeter or 2 centimeters or 1 kilogram or 1 gram. Those are all called units. So the unit that we use for force that we measure with a spring scale is called a newton. The unit that we use for work, what is work? This is a math problem. W equals F times D. W, work, equals force, F, times D, distance. So all it is a simple math problem. But you need to know that work is in joules, force is in newtons, and distance is in meters. When a fan is connected to an electric circuit, it moves, so work was done on the fan. When an object is lifted, it moves, so work is done on the object. A spring scale is used to measure force. Force, including weight, is measured in SI units called newtons, and the newton is usually capitalized. Sometimes it's not. SI stands for the System International, or the System International. And of course, these are all examples of spring scales. Ours looks more like this, but it's made by the Ohas company. So you needed to make sure that you have a spring scale is used to measure force. Force, including weight, is measured in the SI unit called newtons. Let's think for a moment. We are going to write yes if the example demonstrates that work is being done, or no if we think work is not being done. Now remember, we are talking about scientific work. So we're looking for some force moving an object a distance. If an object is not moved a distance, then we're going to say no. If an object has a force that moves if an object has a force and it moves a distance, we'll say yes. Let's look at the first one. What about a child playing on a swing? When a child is on a swing, is a force moving an object a distance? Well, we're on a swing. The force is usually you kicking off with your feet or someone pushing behind you. Does the object move a distance? And is there a force? If the answer is yes to both, then you put yes here. Yes, of course you would put yes. Of course, when you're on a swing, you are moving an object a distance. What about a mother holding a baby? A mother holding a baby, is there a force? Yes, there's a force, but is it moving an object a distance? If the mother's just holding the baby against her, there's force to squeeze the baby to her, but is she moving it anywhere? It doesn't say she's rocking the baby. It just says the mother's holding a baby. So is there a force? Yes, she's holding the baby to her. But is the object, the baby, moving a distance? You're right, it's not. So can we say that the mother holding a baby is the definition to scientific work? Exactly. No, it's not. So in the first space you put yes. In the second space you put no. What about this one? A weightlifter holding weights over his head. Now we have to think about it. Is there a force? Well, he's holding weight over his head. Is there a force? There has to be a lot of force to hold it over his head. But is the object moving a distance? Exactly. Of course not. It's not moving because he's holding it above his head. So you have to say no. No work, no scientific work is being done. So far it should have said yes, no, no. Yes, no, no. Now let's look at the next example. Writing with a pencil. Well, is there a force? Yes, my hand is forcing the pencil to write. Now, is there an object moving a distance? Yes, the pencil is moving across the paper. So you know that it's moving a distance. You know that there's a force. You know that there's an object moving a distance, and therefore your answer is yes. Now let's look at the last example. Thinking about a math problem. Is there an object being moved a distance with a force? Thinking about a math problem, is there a force? Is there an object moving anywhere? Exactly. Thinking about a math problem might feel like work, but in scientific world it is not. It is not considered work when you just think about a math problem. It might make you mentally exhausted, but physical exhaustion is not something that you feel because it really wasn't scientific work. So your answer to the last example is no. Simple machines. We're going to move on and talk about, well, how does work apply to our life? Well, there are 6 simple machines that most people memorize. And some people memorize a 7th, the gear. But we're going to focus on the simple machines that we need to memorize for South Carolina standards. The first one that we should focus on is a simple machine. A simple machine is a device that helps reduce the amount of force required to do work. I said reduce force. I did not say it reduces work. I need you to make sure that you memorize that it helps reduce force. Put a big star by that. Reducing force, reducing force. Of course, of course, of course, of course. What does a simple machine do for you? A simple machine reduces force. Of course, of course, of course, of course. Simple machine reduces force. Of course, of course, of course, of course. You need to memorize that. A simple machine reduces the amount of force required to do work. What kind of work? Scientific work. Work is done, again, as we are going to remember this, when a force, the effort force, is applied over a distance. So work equals force times distance. Make sure that you filled in each of the yellow sections into your answer sheet. A simple machine allows the user to apply a smaller force over a larger distance to move an object. What am I talking about when I say a smaller force? Well, look below. There are 2 different inclined planes. What's an inclined plane, you ask? Well, it's one of our simple machines, and it's also what you would see if you were going at a restaurant and you saw a handicapped ramp. Another example of a simple machine that's an inclined plane is stairs or a ladder. So if we were looking at this handicapped ramp, and let's say that, or just a ramp that you're moving things, if you were moving into a house, would you want to go up the ramp that is super, super steep like this? Or would you want to go up a ramp that is more graduated like this? Well, does work look any different? Remember, I told you, work is a math problem. It doesn't matter who your math teacher is. All of them teach you how to multiply. Work equals force times distance. Multiplying's pretty easy. If the force was 100 newtons and the distance was 2 meters, then 2 times 100 is 200. And remember, at the very beginning I told you, when we get an answer for work, its unit is in joules. So if this man were moving this safe up a 2-meter high inclined plane, he would use a force of 100 newtons to push it up. 100 newtons times 2 meters equals 200 joules. So work equals 200 joules. Now that is an inclined plane that's tall, very steep. Now let's look at work in the less steep one, the shorter one. So work, let's see, it took 50 newtons. Over here it took this guy 100 newtons to move it up the steeper one. But over here his force was less. He only had to use 50 newtons because it was less graduated and very easy for him to get up. Now, it did have to be stretched out. This one was shorter. It was only 2 meters. This one had to be long, and it was 4 meters. So the longer you make the inclined plane, the less steep the inclined plane needs to be. So what did it make easier? Force. His force was less. But let's do the math problem now. So work equals force times distance. Well, the force was only 50 newtons this time, but they had to stretch it out over 4 meters. 4 times 50 is 200. 200 joules is how much work there was. Oh my word! Look at the difference. 200 joules. 200 joules. There isn't a difference whenever you get the answer for work. What's the only thing that you noticed was different? That's right. The force is less and the distance is more. Over here, the force is more and the distance is less. So, you need to think seriously about what happens. I told you right up here, a simple machine, of course, only reduces force. So, a simple machine reduces force required to do work. It doesn't reduce the work. The work was the same. It was 200 joules here, and the work was 200 joules here. What was reduced? This went from 100 newtons to a 50 newton force. So, a simple machine, of course, always help to reduce the force required to do work. Now, we are going to see what happens next. Simple machines can also change the direction of the force applied. If the distance over which the effort force is exerted is increased, the same amount of work can be done with a smaller effort force. In other words, simple machines are going to help us, and we can use the simple machines to make life easier. The design of our simple machine can reduce the amount of force required to do work. Let's go back and make sure that you get these copied. Simple machines can also change the direction of the force applied. If the distance over which the effort force is exerted is increased, the same amount of work can be done with a smaller effort force. The design of the simple machines can reduce the amount of force required to do work. A lever is a rigid bar or a board that is free to move around a fixed point called a fulcrum. The fulcrum may be placed at different locations along the bar. Eventually, we will investigate the Simple Machines gizmo in class. It will deal with levers and all of the other simple machines that we're going to be looking at. Make sure that you write that a lever is a rigid bar or a board that is free to move around a fixed point called a fulcrum. The fulcrum may be placed at different locations along the bar. So at this point, you should have these answers filled in on your sheet. A lever is a rigid bar or a board that is free to move around a fixed point called a fulcrum. The fulcrum may be placed at different locations along the bar. A lever can be designed to reduce the amount of force required to lift a weight in two ways. And I'm going to show you a picture of that in just a moment. Now you should have had that work equals force times distance. Now what should we have written here? The work equals the force, so you should have written 100 newtons times 2 meters equals 200 joules. Very good. And down below you should have said 50 newtons times 4 meters equals 200 joules again. A lever can be designed to reduce the amount of force required to lift a weight in two ways. By increasing the distance from the fulcrum to the point where the effort force is applied, or by decreasing the distance the weight is from the fulcrum. That sounds so confusing. Let's explain it a little clearer. Any place that is right underneath the lever, like the point that it's changing, that is called the fulcrum. It's called the pivot point. Wherever it's pivoting. So if I were sticking this board or this stick and I was trying to pry up this rock, I would use this one. Do you see the little triangle right there? The little yellow triangle is what we call the pivot point or the fulcrum. It just means where are we pivoting? We're trying to fling this rock up in the air and move it. And so we use basically what we have. We use a stick, we prop it against the other little tiny rock, and then we try to move the big boulder. So we are pushing down, we're pulling down on the stick. See, the blue arrow is always talking about the effort. I'm pulling down with my hands. The yellow arrow is always talking about where is the fulcrum or the pivot point. And the thing that we're trying to move is called the load. So the load's either going to move up or it's going to move over this way or down this way. So the load is what you're trying to move. Now, it said that we could either increase the distance from the fulcrum to the point where the effort force is applied. So we could increase this ramp. We could either move the fulcrum this way or we can move it this way. Or we can decrease the distance the weight is from the fulcrum. Let me show you a couple more examples and you'll understand that a little bit better. By increasing the distance the effort force moves relative to the distance the weight moves, a lever can reduce the effort force needed. So in this picture, blue was the effort force, so she's pushing down, and it could be a guy, but I'm saying she because I'm imagining that I might be doing this. I am pushing down on my screwdriver. So there's the effort, the blue arrow. The little yellow triangle is right here at the end of the screwdriver. That was my pivot point or my fulcrum to prop the can lid up. What was the actual load? The lid. I pulled the lid up with it. So that was the load. Now over here, the fulcrum's way over here at the actual wheel, because you can lift up or you can lift down. So he's lifting up, that's the effort force. And when he lifts up, he's holding on to a lever. The lever is right here in his hands. There's actually several simple machines incorporated into a wheelbarrow, but we'll talk about that later. So he's lifting up on his lever. It's tilting the load, which is inside the container, and the pivot point that allows it to also lift up is the wheel. In this picture, he is golfing. His pivot point is actually his own shoulder and arm. The little yellow arrow is there. And the effort force is when he swings out on the golf club. And what's he trying to move? The actual golf ball. So that's the load. The next simple machine is a pulley. We see pulleys every day. We just might not think about them. One of the most common places in a school to see a pulley is on a flagpole. A flagpole is a fixed pulley. Fixed means it's fixed at a certain point. It's stuck. It's not going to move. A fixed pulley has a pulley has a grooved wheel with a rope running along the groove. Pulleys can change the amount and or the direction of the force applied. That's of course called the effort force. These same colors are used whenever we are talking about pulleys. There's the blue arrow, there's your effort force. Pulling down on one of the ropes on a fixed pulley allows the other rope to go up. So on a flagpole, you pull down with the effort arm or the effort force. Pulling down on one rope allows the other one to go up. So really all that a fixed pulley does is changes the direction of your work. In order to get the flag up, she pulls down. It's very simple. So pulleys can change the amount and or the direction of the force, the applied effort force. By arranging the pulleys in such a way as to increase the distance that the effort force moves relative to the distance the weight moves, a pulley can actually reduce the effort force needed. Now, in a fixed pulley on a flagpole, all it does is changes direction of the force. It doesn't make anything, it doesn't decrease the effort, it just changes which way the effort goes. So a pulley that's a fixed pulley only changes the direction of the effort. It does make it easier for you because it's changing the direction of the effort. But whenever you add more pulleys and you arrange them in a different way, you could do something that seems somewhat impossible, like what you see below. If you look over here, you'll see just a simple girl pulls down, her effort pulls toward her on a chain, but this is called a block and tackle pulley system. Here's a pulley and here's a pulley. And they fix them in such a way that this girl all by herself can move it's just a humongous engine that weighs hundreds and hundreds of pounds that usually takes like 3 men to move, but she's able to do it simply by pulling on a chain. So by arranging the pulleys in such a way as to increase the distance that the effort force moves relative to the distance the weight moves, a pulley can reduce the effort force needed. Movable pulleys are used to reduce effort force. So in the case of the flagpole, a fixed pulley, it only changed the direction of the force. But in the case of a movable pulley or a moving pulley, it definitely reduces the effort force. A single fixed pulley changes only the direction of the force. You pull down and the weight goes up. We've already talked for a moment about an inclined plane. An inclined plane is a sloping surface like a ramp that reduces the amount of force required to lift an object. As we can see here, the little handicapped student tries to go up the steep ramp and he looks like he's having a very hard time. It's 5 meters long. But if you just would stretch out that ramp a little bit further and make it double the size, he was able to speed up there quite easily. It's 10 meters long. It's still, they're both still 1 meter high, but when you move the distance and stretch it out further across more of a distance, it allows the work to be done with less force. An inclined plane can be designed to reduce the force lifted to lift a weight in two ways. A, either increase the length of the ramp, or B, decrease the height of the ramp. So 1, increase the length of the ramp, or 2, decrease the height of the ramp. So we can either make it less high, or we can stretch it and make it longer. By increasing the distance the effort force moves, the length of the ramp, relative to the distance the weight is lifted, the height of the ramp, an inclined plane can reduce the effort force that we need. So again, inclined plane, ramp, increase, decrease, reduce. At this point, you should be able to take a moment and draw a diagram of a lever where the fulcrum makes it easier to pick up this box. And then on this side, draw a diagram of a lever where the fulcrum makes it harder to pick up the box. Your teacher might need to do an example with you in the next day or two, and that might be a little bit more clear to you. We're going to make sure that there's a piece of wood sent around and a little chunk of wood, and then we'll have your teacher demonstrate this for you. So I guess hold off on this for right now. Sometimes simple machines are added together to make a big compound or complex machine. Now, in South Carolina standards, a compound machine and a complex machine are the same thing. Basically, all you have to memorize is that a compound or a complex machine is something that is more than one simple machines added together. Levers that have the fulcrum between where the effort force is applied and the weight is located can be found in tools. For example, a pair of scissors are two levers working together, and a crowbar. Levers that have the fulcrum on the end and the effort is applied in the middle to lift a weight on the other end can be found in tools. For example, tweezers. Tweezers are what girls use to pluck out their eyebrows. Two levers working together, or even a broom. Levers that have the fulcrum on the end and the effort force are applied on the other end to lift a weight in the middle can be found in tools. For example, a wheelbarrow or a bottle opener. So if you see, there's a lever on this end, a wheel, an axle here, and then of course in the center you have your load. A bottle opener, well, everyone knows how one of those works. Pulleys that are fixed, meaning that they are attached to a structure, can be found at the top of a flagpole or on a window blind. Pulleys that are movable, meaning that they're not attached to a structure, can be found at construction cranes or on construction cranes as part of a block and tackle system. Inclined planes with a sloping surface can be found as ramps on a truck or wheelchair ramps and stairs. Inclined planes that are wedges, one inclined plane or two back-to-back, inclined planes that can move are found as knife blades or nails. Inclined planes that are wound around a post or cylinder are called screws. Screws can be found in bolts and jar lids. If you look right here, the wedge on this axe is actually two inclined planes moved next to each other. They're put back to back. And I'll give you examples of that in just a moment. See, an inclined plane reduces force needed, not the work, but the force, by increasing the distance the object moves. Remember, an inclined plane is a mom, and the wedge and the screw are her babies. Why do I say that? See this inclined plane? If we took this one and we put it back to back, we put one on this side, one on this side, we'd make a wedge. That's what an axe is. At the very end of the axe handle is the blade, and the blade of an axe is actually a wedge. The blade of a knife is a wedge. Or even scissors, the actual cutting part. Now, if I were to take this and wrap it around a cylinder, I would make a screw. Do you see this inclined plane wrapped around and around? Each of your teachers will demonstrate this with a piece of paper and a cylinder in the next day. So the inclined plane is a mom. And who are her babies? A wedge and a screw. Because an inclined plane back to back makes a wedge. So two inclined planes back to back make a wedge. So that's why this is its mother. An inclined plane is the mother. Two inclined planes back to back make a wedge. And one inclined plane wrapped around a cylinder make a screw. So that's why screw and wedge are the babies of inclined plane. So there are two types of pulleys you have to know. The single fixed pulley only changes the direction of a load. It doesn't reduce force. Flagpoles and clotheslines are examples. And then there's the movable pulley, like a block and tackle that lifts an engine. It does reduce force needed to move a load. And these are examples of them. The single fixed pulley, as in the flagpole, and then the movable pulley, like you see here, lifting such a heavy load. The lever, and here's a lever, here's the fulcrum. Where would I press down with my effort to make this move up? Would I push way over here, or would I push closer? The fulcrum is right here. If I wanted to move this heavy rock, would I push real close with effort real close to the fulcrum, or would I push down way over here? That's right. I would push down way over here, and it would make my effort less to lift that heavy load. Now, did you know that your arm is a lever? Your arm is a lever. Your elbow is the fulcrum. Everybody, bend your elbow. Look at your arm. I want you to put your pencil or your pen in your hand. And I want you to squeeze it. And then I want you to take your other hand and put your fingers in the opposite section of your elbow. So in other words, right where your arm would bend, right here. I want you to put your fingers right here, and I want you to bend your arm up towards your hand, up toward your head. Bend it up and down. So your elbow is the fulcrum. Your muscle, the part right here, is your effort. And what's inside your hand is your load. So don't forget that your own hand is a lever. And then there's the wheel and axle. You've been knowing what a wheel and axle is since you were a little kid. A wheel rotates and the axle passes through the center of the wheel. All of these that I've gone over are simple machines. What I haven't gone into detail with is sometimes people call a gear a simple machine. Let's look and see what one looks like. So there are 6 simple machines, but some people include the gear to make 7. The lever, the wheel and axle, the pulley, the inclined plane, the wedge and the screw, and some people include a gear. And a gear really looks like a wheel and axle with just a little bit of other things attached to it. So a gear kind of has little levers on the outside of it that make it go round and round and interconnect. Remember that simple machines, compound and or complex machines reduce the force and the distance traveled. The amount of work always stays the same, only the effort force ever changes. And a compound or complex machine is more than one simple machine put together. Remember too that in order to have work, energy is needed to do it. No energy, no work. So if you don't have any energy, and energy is the ability to do work, then you can't have work done. Work equals force times distance. Joules is what work is measured in. Force is measured in newtons and distance is measured in meters. The units are work is joules, force is newtons, distance is meters. So inclined planes with a sloping surface can be found as ramps on a truck or a wheelchair ramp and stairs. Inclined planes that are wedges, one inclined plane or two back-to-back inclined planes that can move, are found as knife blades or nails. Inclined planes that are round around a post or a cylinder, and they're called screws. Screws can be found in bolts and jar lids. Wheel and axles consist of two circular objects, a central shaft called an axle, inserted through the middle of a wheel. Wheel and axles can be found as doorknobs, steering wheels, screwdrivers, gears, and bicycle wheels. And here is the inclined plane wrapped around a screw. An inclined plane wrapped around a cylinder makes a screw. So this screw is created by wrapping a little metal inclined plane around a cylinder. Finally, complex machines are known as compound machines. They consist of two or more simple machines. Examples may include scissors, consisting of two levers and two inclined planes. The levers are what you put your hand in and you control and move it. And the inclined planes are the wedges that cut. A fishing pole consists of a lever, a wheel and axle, and a pulley. A bicycle consists of levers, handlebars and handbrakes, wheel and axles, which are gears, wheels, and pedals, and a number of screws. There's so much to learn in this unit. I hope that you can really concentrate on it. Make sure that all week you're studying. Thank you.